Okay, let's start learning how to use Mohr circle to find stresses and on any arbitrary plane. Now, the given that we've got here is a state of stress that's represented by these normal and shear stresses. We're first just going to construct Mohr circle, and then we'll start talking about how to use it, for instance, to find the normal and shear stress on this inclined plane, as well as maybe finding the principal stresses and maybe the maximum shear stress along the way. There's just a whole host of things that can be found here. Right? So the first thing to do is actually to create an axis for yourself, or maybe actually the first thing to do is make sure you've got yourself a circle template. Right? This is one such template. It's got very small circles all the way up to about 2 1/4. Sometimes that's plenty good. In fact, most of the time that will be good enough, but every once in a while you're going to want bigger circles for your drawings, and so here's even a larger template. You'll also probably find that it's convenient to have a square template to draw the stress cube. You can do it, of course, out of just a straight edge, but oftentimes it's easier to work with that. Now, the thing about Mohr circle is sometimes you want to kind of think ahead to how this is all going to play out. And one of the things that you'll always end up doing is selecting 2 points that are on planes that are at perpendicular orientation. So for instance, let's take this vertical plane, let's call that point A, and it has a 6 KSI normal stress that's in tension. So I'm just going to write down 6T, and it has a 4 KSI shear stress. But which direction is it going? Well, what we do for Mohr circle is think about a pin being placed right here in the center, and this little red arrow on that plane that A represents would tend to want to spin this in a clockwise fashion. So write that down as clockwise. So that's point A. Now on the other plane, at point B up here, right, now B would have a 10 KSI compressive stress, and it has a 4 KSI counterclockwise effect. These two will always be opposite each other because these shear stresses have to be set up in a way that create equilibrium from a rotational kind of standpoint. These are 2 points that we're going to plot that we're going to use for the creation of Mohr circle. That's all we're going to really need. And when I look at that, I see that, okay, we've got units of 4 on the torsion, which isn't too big compared to the 6 and the 10 for the normals, but these two are far apart from each other, right? One is 6 tension, one is 10 compression. That's going to turn out to be a pretty big circle, and you're going to see why here in just a second, right? So that means the radius or the diameter of the circle is going to be pretty large. I'm going to end up probably needing a lot of space. And the first couple of times you do these, you're probably going to make some mistakes along the way graphically in terms of the scale of what you want to do or how to sort of fit it on here. I know from a little bit of experience here that 6 is, of course, smaller than the 10 compression, so I'm going to put my vertical axis that represents torsional a little bit shifted to the right. Will probably be a good idea to start with, right? And you're like, what the heck are you doing? All right, the horizontal axis, remember from our model that we had for Mohr circle, looking for it, here we go, is the stress transformation equations could be rewritten that sigma n minus the origin, which is the sigma average, quantity squared, plus the torsion stress, that's the y value squared, equals this radius, right? So the way we're going to really do this, let me pull that back again, is we're going to basically plot a point on this side, plot on that side. They're going to be diametrically opposed. Draw the line for the diameter, and we can construct everything else as we go. Like, what? All right, so let's build it up. Horizontal axis is the normal stress. Tension to the right, compression to the left. We're going to plot shear stresses on the vertical, clockwise up and counterclockwise down. There's going to be some great advantages to doing it this way that you'll start to see in just a little bit. right? So we've done this. Now we got to choose a scale for the plotting, right? And I'm looking at this. You can't see on screen easily the engineering paper grid work that is behind, right? But I can see it by eye here. And with 6 4s and 10s running around, I'm going to let one little grid be my unit base. And so there's 5 squares to an inch, it turns out. And so that's going to put a 6 right there. 6 tension, 4 clockwise. 1, 2, 3, 4. That's 4 there. And that's 6 from the, nope. Yeah, that's 6 from the origin there. So that is point A. Point B is at 10 compression. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're going to go down 4 because counterclockwise is down. 1, 2, 3, 4. Come over. And there's point B. So there's the 4. There's the 10. Right now, the total distance between that is 16. So the origin is at 8 over from either one, which globally would be at 2 away from the origin, right? So 8 plus the 2 is the 10. And that is the center of our circle. So we'll draw the diameter line. Now, how the heck do I know that that's really the case, that those are diametrically opposed like that? That goes back to our overall stress transformation equations, right? We had the 2 theta business in here. 2 theta on cosine and the sine term. So in real life, these 2 points are at 90 degrees apart. You put them into Mohr circle, and the equations operate with twice as fast, right? So what's 90 degrees apart in real life on Mohr circle is 180 degrees apart. Isn't that pretty cool? So that deforms the diameter. Now, what you do is you try to find a circle that fits that. This one doesn't because I chose too big a scale. So that's why you do this kind of a template. And let's see if we can get one close. That's kind of close, but not perfect. Let's see if this one's a little bit better, and it is, fortunately. And so now we can draw the circle in pretty good quality here. And when we're drawing this, note what we're doing is representing graphically this function that is this stress transformation, that combination of normal stress and shear stress on every single plane, right? Wow, wait a minute, what? That is a plot of this equation here. So for every x and y combination that matches a circle that has its origin here, that's the sigma average, and then the y thing is whatever the shear stress is in that plane, and that gives us the normal stress. So wow, that's pretty interesting. So that means that our sigma average here is equal to a 2 compression, or minus 2 KSI, right? Where plus equals tension, right? And that's interesting. Right, now that's the radius, right? Boom, 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 that's the radius. Now, gee, what angle does that make? Well, let's take a look. That we have a right triangle here that is 4 units high and 8 all the way along there. So the angle that would go from point A down to this point that it would sweep through, that turns out to be theta P1, right? The angle from point A over to the principal plane. So theta P1 is equal to the arctan of opposite over adjacent, which is 4 over 8. Don't really care about signs here right now. So that's, of course, 0.5, and take inverse tangent, and that's 26.56. Now, the thing about that, let's just call it 26.6, is that that's really twice the real angle, right? Because in Mohr circle, everything is twice. That all comes back from the original stuff over here. So the real theta then gets doubled in Mohr's circle. So that means that our theta P1 we really want is 13.3 degrees. We'll use that later on. Notice here's your principal stress. Boom, it's right there. It is at -2 plus the R. We haven't calculated the R yet, but we can do that. R is going to be the square root. Oh, it's just this triangle, right? So square root of the 4. No, let's just do it as the base. That's 8 squared plus then the 4 squared, square root. And so that would be 64 plus 16, and square root of 80 is 8.94. Repeating. And so 8.94 minus, that would be this whole distance here minus the 2 would get us to a net of 6.94, and that's your sigma 1. That's one of the principal stresses. Over here, we go 8.94 and add it there, the 2, so that's actually 10.94 for sigma 2. Of course, in units of KSI, this one's compression, that one's tension. We'll come back to that. The maximum shear stress is up here at the top or bottom of the circle. And, well, that's just the same thing as R. So tau max is going to be our 8.94 KSI. Well, which direction? Well, it depends on which plane you want to look at in terms of which direction, right? So that's the beginnings of how we might use Mohr's circle. If we wanted this specific angle or the stresses at the specific angle of, that would be 15 degrees from that horizontal plane that B is on, 15. So notice, to go from B to that plane, we're going to rotate in a clockwise fashion, 15 degrees in real life. In Mohr's circle, that means 30 degrees. So here's point B, and we're going to go 30 degrees on Mohr's circle. Now, we know that this angle on Mohr's circle is the 26.6, so we're going to go past that by just a little bit. And so schematically, that new plane would be represented. This is going to be not quite at scale. If you wanted to measure it graphically, you could. You got to get a protractor out there, but we don't need to do that. We just need to get it notionally set up correctly. That whole angle is our 30 degrees. This leftover angle is going to be 30 minus the 26.6. So that would be what, 3.4 degrees, right? And so that'll allow us to figure out what's going on here in all these various values, right? So we know the radius, that's the 8.94. So this combination of normal stress and shear stress is going to be, well, the base of that triangle is R times cosine of 3.4. So 3.4 times cosine is going to be almost 1, but not quite, 0.998, times our radius of 8.944, and that's going to be 8.928 plus the 2, so we'll have 10.93 rounded for the sigma. The tau would be the sine value there, so 8.944 times our 3.4 degrees sine, and that equals 0.53. And that's our normal stress and our shear stress on this angle. The normal stress is compression. The shear stress is on this upper portion, so that's clockwise. And so if you really wanted to show that little portion of the stress cube that represents that one right there, then at least for just that plane only, what you'd have is, there's your 10.93, and clockwise means that that one is going that way at 0.53. Now, if you wanted to complete this all off, you'd go to the other side you have the compression, and let's see, that's 180 degrees, so twice that is 360, puts us back at the same place. So clockwise again, that way, that way. What about those points? Well, those are at 90 degrees in real life, so 180 here. So that means 180, we scoot over to here. And we already know the shear stress. It's got to be the 0.53. Notice it goes into the counterclockwise side of things. So once again, the shear stresses always pinch at the corners. And then it's just about what that normal stress is, right? Well, we had 8.928 was from here to here. So that's also 8.928 here, but we got to subtract off the 2 for that average. So 6.93 rounded, and that would be in the tension side on that one. And that's how you find a complete state of stress on the stress block associated with this 15-degree inclined plane. And we also found out what the principles were and what the max shear stress is. We didn't draw the stress blocks that went with them, but that's how you construct and begin to use Mohr's circle.